Hi. One thing we can be sure of is that we know more about the universe today than we did 500 years ago. So why is that? Is it because there's been a series of brilliant astronomers having brilliant ideas? Well, yes, partly it is that, but it's also because there's been a series of technological revolutions that astronomy has benefited from. Now, history is pretty complicated, but we're going to boil this down into 6 key steps. Revolution number 1, the invention of the telescope. Now, to a sailor, the telescope is all about magnifying the image, making things look bigger. But to an astronomer, telescopes are all about catching more light, so we want them to be big. Now, the pupil of the eye is about 5 millimeters across. On the other hand, if we take a pair of binoculars like this, or a small telescope, that lens there is about 50 millimeters across, so it collects 100 times more light, can see things 100 times fainter. On the other hand, here, this lovely teaching telescope that we have here at the university, the mirror of the telescope here is about 50 centimeters across. So that's another factor of 100 in its light gathering power. Now, big professional telescopes can be anything from 2 meters to 10 meters across, and so they collect even more light. And right now, the world community is developing a giant new telescope which will be 40 meters across, which with great imagination is called the Extremely Large Telescope. And so we can catch more and more light and see fainter and fainter objects. This produces technological challenges, however. We'll be looking at those in week 2. Okay, revolution number 2, spectroscopy. In the 17th century, Isaac Newton first took light, put it through a prism, and split it up into its component colours into a spectrum. So today we tend to do the same thing with diffraction gratings rather than prisms, but it's the same basic idea. And in the intervening 350 years, spectroscopy has been possibly the key technique for physics, for chemistry, and even for biology. It tells us about the structure of matter. But it was the Victorians who first had the idea of pointing a spectroscope at the stars. This was first done by William Huggins at Tulse Hill in London, and also by Alberto Secchi at the Vatican Observatory in Italy. And what they saw was a revolution. By breaking up the light into its spectrum, we were now able to tell what stars were made of, how hot they were, and even how fast they were moving. It's really the point in history where astronomy became astrophysics, and it's been a key technique ever since. Now, the sort of spectrographs we bolt onto the back of telescopes now are very big, and they're very tricky to design, and that's something we'll be talking about in week 6. So, revolution number 3, photography, another great Victorian invention. Let's have a look at this photographic plate that I've got on the light table here. Now, photography did 2 things for astronomy. The first was it enabled us to get an objective image, to record an image permanently. So we didn't have to rely on some dodgy astronomer's sketch. We could simply see, anybody could see what that part of the sky looked at by looking at the photograph. So that's advantage number 1. Advantage number 2 is that astronomers were able to integrate, that is, to keep exposing the plate, adding up more and more light to see fainter and fainter objects, and this plate goes pretty deep. Now, the human eye, when we're receiving information, it feels like a continuous movie, but actually, of course, we're integrating for 1/25th of a second on the retina. Pretty soon, astronomers with their glass plates were keeping them bolted to the telescope and exposing them the whole night. Now, today we don't use photographic plates anymore, but we use another solid state detector. This is what we use most often. It's a CCD. This is pretty much the same as the detector in your phone camera, but it's considerably bigger and also more efficient. So that's the CCD camera. Now, astronomers now like to make even bigger cameras by putting lots of them together in a mosaic. You can see that in this picture here of the Pan-STARRS camera in Hawaii. That's a gigapixel camera and covers a large amount of sky in one go. CCDs are also very efficient. They catch more of the light, and so we can go deeper and deeper. We also have similar detectors that, for example, work at infrared wavelengths. And this picture you're seeing here, this is the ultra-deep survey made on the UKERT telescope. That involved adding up data, effectively exposing for hundreds of nights. Revolution number 4 is a 20th century revolution, the revolution of multi-wavelength astronomy. Now, light is an electromagnetic wave in space, and the lengths of the waves can be very different. They can be little tiny nanometer length waves, or they can be great big long meter long waves. It covers a big range. Now, what we refer to as light normally, visible light, just happens to be a small range of wavelengths that we can detect with the retina of our eye. But there's a lot more out there. Radio waves, infrared, ultraviolet, X-rays, they're all light, but they have very different wavelengths. Now, if we're going to detect those different kinds of light with something other than our eye, we need completely different technologies for each of those wavelengths. So the story of the 20th century was one of opening up wavelength windows and seeing the universe in a different way, in the ultraviolet, in X-rays, in radio, and so on. And every time we opened up a new window, we saw completely different objects, and the universe seemed very different. We discovered relativistic jets, spinning neutron stars, gas at millions of degrees, something weird every time we tried something new. Revolution number 5, space astronomy. Arguably, since the 1960s, this is the thing that's made more difference than anything else to our understanding of the universe. It's the ability to launch things into space. So here's a picture of the Hubble Space Telescope being launched on the space shuttle. And here's another picture of the Hubble Space Telescope actually in orbit, taken from the space shuttle. So it makes an enormous difference, but it's very, very expensive. So why do it? For the same amount of money, we could build a much bigger telescope on the ground. So why launch things into space? It's because the atmosphere is our enemy. So the atmosphere does 3 very bad things which annoy astronomers. The first thing is that it blocks some of the light. Some particular wavelengths, for instance X-rays, don't get through the atmosphere at all. So in order to do X-ray astronomy, we have to launch rockets into space. There's no choice. The second bad thing that the atmosphere does is to distort the light. As it comes down through the atmosphere, it wiggles about and it blurs our images. So it means that our pictures are not sharp. And that's the biggest reason why the Hubble Space Telescope was put into space, is to take sharper pictures. The third thing is that the atmosphere glows. We're trying to see extremely faint things in astronomy, and when there's a background glare from the sky, it makes seeing faint things extremely hard. So even though space astronomy is expensive, it pays dividends once we get things up there. We'll talk more about space astronomy in week 3. So, revolution number 6 is the one we're in right now. That's the computer revolution. So this started in the 1960s, but really started to take off in the 1980s. Now remember we talked about the photographic plate here that enabled us to record images permanently, and the modern version of that is the CCD detector. But the additional thing about the CCD is that it's electronic. So when we take the electronic signal and we combine that with a computer, it means that we store the information as numbers on a computer. Once they're numbers on a computer, we can do anything. We can do calculations, we can play with it, we can just do whatever we want to. So that's when things really took off for computers. Now at the same time as the observers were playing with their detectors and computers, the theorists were getting into computers as well. they took extremely big computers and ran calculations based on their theories of how they thought the universe should look if the theories were correct. They simulated entire universes and are still doing that today. A lot of astronomers do this. This movie that you're looking at now is a simulation of the universe made by the Virgo Consortium. And the challenge is to try and compare that to our observations of the real universe to try and work out if the theories are correct. So the stage we're at now is trying to join together data sets, including theoretical data sets, from across the whole World Wide Web and to turn them into one giant seamless whole. And that challenge is known as the virtual observatory.